We are, I was hoping that I can zoom through a few things very quickly to get you the flavor of the mindsets of folks in the industry, how they develop the technology. Because it's something that I had the privilege to go through, but in most cases, most of you would not have, or may not have, may or may not have the privilege to do that. Because I happened to be at a time when the silicon technology was at the beginning. And I was lucky enough to be in a position where we could do all kinds of experiments to make things happen. And those are very hand-on experiments. And historically, some of the people who wrote some excellent books on process and device technology, many of them had at least some exposure in the industry first, and then went back to academia to put their thoughts together. And those textbooks that I had given you a list of, those are some of the fairly established books that is being used in various universities in different parts of the world. So whatever I don't touch upon here, you will see a good bit of it in those books that I have mentioned to you as as your pastime reading or side reading or whatever. So I do encourage you to read those. But because of the time constraints, I'll try to emphasize things that's not in the books. Because you may not have, unless you really delve into it in your entire life, you may not have the chance to have those kind of hand-on experience that industries go through in order to make this technology work and make it happen. So as much as possible, I'll tell you that part of the story, which please. Thank you. So that's why I know one of my motivations is to excite you in the process. And you will then pioneer some mini, micro, from micro to mini, mini to mega at some point, industries for India and for the help of other people in Europe. So with that, thinking of my aspiration, I am really glad to present you what I know and take you through. So a lot of simulation part I purposely avoided because you have other people who will assist me, Partha Sharati, and Omrita. I have spoken with them and I have given them some guidelines of what they would cover for you. And that way I free up a little more time of focusing on more an industrial bias of this VLSI, ULSI technology, which you won't find in the books. So I try to put focus on those while go through the fundamentals wherever I can, so we can have fun together to scratch our brain and figure out why some of these are done and how some of these are these ideas took gel. So with that in mind, I'm covering most of this important part that we illustrated last week in very simple form, what's in the silicon that we put together and integrate. And as we mentioned, this hour is for oxidation, and in the following hour, we will go through the diffusion and, if possible, ion implantation. So, I'm going over fairly quickly some of these topics because my intent is to delve into the nitty-gritties of how technology is developed, how we have our mindsets to develop the technology, and where the outcome is, and where we face some hurdles and how we solve them. So those kind of things is something would interest you, because in future, when you get into those predicaments as pioneers of some industries and develop something for others, you would face similar questions. And if my experience is any guide, we learn a lot from mistakes. It's the mistake which gives us a better edge. It's the failure which teaches us how to climb the hill. So, with that in mind, let's go through this period of what some of the salient features of oxidation, and then in the afternoon hours we'll go through diffusion and possibly ion implantation, if we can cover those two grounds. Because I'm trying to cover them quickly, some of the basic things, then we can get into some more, the way the industry thinks and develops these technologies. Okay? So, name at least two of the three most critical roles oxide plays in integrated silicon-based electronics. At least two of the three. Which ones? Any volunteer?
Dielectric property.
As an insulator.
Dielectric.
Insulator, of course, yes. No, but in the integration scheme of things, what does oxide, what kind of, remember last week's presentation where we put the oxides, what we did for the oxides to build the devices, right? Just think of that and say, what are the two of the possibly 4 or 5 critical roles, but the two most important roles?
Capacitance.
Oxide is used as a capacitor. Oxide is a very critical element, at least up till the year 2000 as a FET gate insulator. So that's a very important device parameter that we have to handle. No, but in general, in the integrated silicon-based electronics.
So it defines the area of fabrication.
It defines the area of fabrication.
Like it acts as boundary between different layers.
Okay, you mean isolation.
Isolation.
You meant isolation, didn't you? Yes, that of course is an extremely important function of oxide, because it isolates one device, active or passive, to the other device, so that those devices can perform the way we design their objectives and their properties. So that is definitely a very important. What others?
So it protects the wafer while we are making mask, making printing on the wafer.
Oh yes, very, very important. Yes, that's the passivation part of it. There's a passivation layer when we do selected areas where we want to put a particular device and isolate others. It definitely helps you in the so-called isolation in a passivation sense. Remember that I try to identify those devices saying, look, this is the passivation layer and this is the isolation layer. The isolation layer is often deeper because the way we create those devices. And passivation layer is more on the top so that it passivates. So you want to put a certain implant in certain area and not others, so that that can act as a mask, as a passivation mask. Correct. But in the field effect transistor environment, the answer of those two would be, one is isolation, that's a very important role, and the other is, in the field effect transistor, the gates. Gate insulator for the field effect transistor. And in the gate insulator, what makes oxide tick the most is the fact, and superior to anything known to mankind, is that it controls the interface state density. What does that mean? Interface state density.
So the carriers or the number of available states in the channel.
What is interface state density? Can you go into the thinking in the terms of band structure?
So the
Electron states available.
You have a transition from silicon to oxide. And imagine yourself is silicon. Yourself in silicon at the very interface atomic layer. How many bonds silicon shoots up? 4. Now, you have a certain probability that some of those bonds may be as a part of the crystallography, okay, where you have a uniform crystal field. In simple way, we said those bonds are saturated because those electrons are shared. They're shared from silicon to oxygen. What happens to those which are not shared? At the interface, you have broken the crystallographic uniformity of crystal fields, right? That's the interface. The very interface. You have broken. So you have created what we call, in simple way, dangling bonds. Means those electrons, mixed states, are not linked. They're not linked, they're open, they're free. So what does it mean? That means those energies, they create within the band diagram a set of energy states. And those energy states, they're like, think about them in quantum mechanical terms, they're little potential well. There's a well. What does the well do? If you are a blind man and there is a well on the floor, what happens? You get trapped. You get trapped inside that well because the well attracts you. Okay? So, anything attracts you to stabilize that interface. And can you give me some idea? If you have broken bonds, let's assume that you have, of the 4 bonds of silicon, 2 of them are linked to the crystal, 2 of them are free. How many of those means at the surface? What's the surface density? Can you give me an idea? Can you calculate that? I give you that as a simple homework. Calculate the numbers. Figure out. Very simple. What is the surface density of an atom? Okay. And go to the very elemental physics and figure out how many. But I'll give you some rough idea. those free bonds could be as large as greater than 10 to the power 12 per square centimeter. Because they're in the surface, right? They could be larger, significantly larger than 10 to 12. And validate that number, please, for me tonight, when you have some fun with numbers. What does it tell you? That means that interface will attract anything and create a large number of states and can charge up those states. When those states get charged up, then can you control the thresholds? Go back to the threshold equation of the field effect transistor and recognize that if I am putting that many states at the interface where charges get trapped, my threshold is going to be haywire, extremely high. So the conductivity of that field effect transistor, hardly any current will flow, and you have to go to much higher voltage drops at those charges to create the channel, conductive channel, right below the surface, which is the Debye length. Find out what Debye length is, and tell me how Debye length depends on the doping concentration of silicon. All right, but Debye length, let me give you some idea. Debye length is very small. The entire channel is very thin at the surface. So because it's very thin, you have to take care of that interface.